We left off talking about the first of 5 types of reactions, which are pretty common in chemistry, and this one's called, this one's called the precipitation reaction. Now, this is an example of an exchange reaction once again, and up here on the board I wrote AX plus BY making AY plus BX. And the A and the B's are the cations, and the X and the Y are the anions. And what usually happens is AX and BY are aqueous, and A will push B out, if you will. So AY is one of the new combinations, and one of them will create a solid. In chemistry, a precipitate is just a solid that forms in a reaction, all right? And the other one is almost always AQ. So in this example over here, the iron is like A, I guess, and the nitrate is X, and iron is pushing B sodium out, so iron starts dancing with hydroxide Y, and it makes a solid, all right? The FeOH3 is a solid in this case, and the other one, the BX, is just aqueous. Now, you have to make sure that the charges are the same. So this is iron plus 3 here, and it's iron plus 3 there. That's why you need 3 OH minuses to balance that iron plus 3. Same thing over here, Na plus and NO3 minus come together. And when you pull then the spectators out, which are in this case sodium and nitrate ions, you end up with this net ionic equation. Any questions on that? Yeah.
So there could be more than one spectator out?
Yes, absolutely, right. In these cases we're looking at, there won't be any more than 2, okay? But in this case, yeah, both the Na plus and the NO3 are both spectators. Sometimes there'll be just one, but often there will be 2, so good call. Okay, so precipitation means make a solid, but there's more than that. This is an acid-base reaction. So acids are those things with an H plus, and a base is something with a hydroxide. Now, the driving force, the reason why acid bases are so powerful is that they make water. And you might be thinking, whoopee-doo, I can go to the tap, and pull the water out. But actually making water gives off a lot of energy. And the old space shuttles that used to go into orbit, the initial thing that got them off the Earth was the formation of water. They would combine hydrogen and oxygen together to make water. So making water is actually a very energy process. You get a lot of energy out. So in our world then, the driving force of this reaction would be just making water.
Reaction of hydrochloric acid and sodium hydroxide is an acid-base reaction. A color-changing indicator allows us to see that a reaction occurred.
This is the classic acid-base reaction. Sodium hydroxide, most common base. Hydrochloric acid, probably the most common acid. And when they combine, they end up making sodium chloride and water. Now, believe it or not, this is another kind of exchange reaction. The sodium and the H plus here are the cations, and hydroxide and the chloride here are anions. And in an exchange reaction, the cations trade places, or the anions. So the sodium pushes the H plus out, if you will, to make NaCl, and the H plus comes over here and combines with OH to make H2O. But in this context, it might be helpful to think about this as HOH. The H is the plus and the OH minus is the anion, making water. Now, water is a liquid, all right? It's not AQ. If you wrote H2O AQ, it would be water dissolved in water, which is kind of interesting, but it's not very helpful for what we're talking about. Water is a pure liquid, and like we talked about, liquids, solids, and gases stay as they are. You don't break them up. So when you figure out the net ionic equation here, the sodium and the chloride are both spectators, all right? They're both getting pulled out. And the action of the reaction here is literally the formation of water, making the H2O liquid. All strong acids and bases, when they come together, will make that. So up here on this little list, I'm going to put the second one down, which is the acid-base reaction. the generic way to write an acid-base reaction is something like HXAQ plus MOHAQ. And again, the HX is the acid. This is the metal hydroxide, the base. These will also combine. They'll flip each other out. You'll end up with MX, which is just something boring, but more importantly, HOH or H2O is liquid, all right? And this is similar to the precipitation reaction we saw earlier, but while the precipitate makes a solid, the acid and base reaction makes water, and that's enough to make this thing really shine here. Now, acids and base reactions are pretty common. Sometimes these are called neutralization reactions. We'll talk more about what that means in a later class. But the interesting thing is that when you have an acid and a base come together, you always make water and a salt. In this case, the salt is sodium chloride, which is similar to us. It's like table salt. Table salt is sodium chloride. However, it doesn't have to be NaCl. You might be able to make potassium chloride if you started with potassium hydroxide. So in chemistry, a salt is more than table salt, more than sodium chloride. A salt is the product of an acid-base reaction. So a salt will be some type of inorganic compound, something with a cation and an anion. It may be NaCl, but it could also be other things like KCl or KNO3 or blah, blah, blah. So this is the second kind of reaction. Precipitations happen because you made a solid. Acid and base reactions, you end up making water. And both of those provide the energy to make the reactants go over to the product side. Questions? Okay. A third type of reaction is if a gas forms, and there's actually several examples of this, but the one we're going to focus on.
When calcium carbonate, marble, is placed in hydrochloric acid, carbonic acid is produced, which is converted to gaseous carbon dioxide and water in a gas-forming reaction.
This is a super high-resolution camera that shows calcium carbonate and how it breaks down into H2O and CO2. This is more just kind of artistically cool, all right, but it's kind of fun to see what's happening on a really smaller scale. Anyway, this third type of reaction is called a gas-forming reaction. And what usually happens is, I can't talk and write at the same time, obviously. What usually happens here is you start with a metal carbonate. A carbonate is CO3 minus 2. So if you have a metal with it, like calcium, sodium, potassium, whatever, you have a metal carbonate. And you'll take an acid and add it to it. And what happens is you end up with some kind of ionic compound, but here's what you want to look for. Carbonic acid is H2CO3, and H2CO3 is an unstable acid. The unstable acid, carbonic acid, actually breaks down into CO2 and water. So if you were writing this reaction up here with calcium carbonate, you could write it generically as MCO3 because it's a carbonate, it's a metal carbonate, and you're reacting it with some type of acid. I'll write it as H2, no, let me rewrite that. You'll add it to 2HX aqueous, which is the acid. And just like the other ones, the M and the H are going to trade places with each other. So you end up with some type of MX2 aqueous, which you can care less about. But what's really interesting here is the H2CO3. And this is an acid which doesn't stay around together very long. It actually breaks up into H2O liquid and CO2 gas. So the H2CO3 does not break up, does not stay together, it breaks down. And we'll talk about this here in a little bit. This is the main gas-forming culprit we're going to see in this class. The carbonic acid does break down, and you'll actually see little bubbles and stuff come off. Now, in lab this Wednesday, we're also going to see some examples of ammonium hydroxide, and that's another unstable system. This one breaks down into ammonia and water. This is actually an unstable base, if you will. So let's back up here a little bit. The third type of reaction, gas-forming reaction. The driving force is you're making a gas. However, when you do the exchange, it may not look like any gas is formed. So as you as the students then, look for H2CO3 or NH4OH. Because if these are products, they won't stay as products. H2CO3 will break down to CO2 and water. NH4OH will break down into NH3 and water. And in the net ionic equation, you should not write H2CO3 or NH4OH as products. You should write what they break down into. Any questions on that? Okay. So here's an example question. It says, which equation represents the net ionic equation and balance for the reaction of magnesium carbonate with nitric acid? Now, A right here, if you think about this long enough, A is actually the balanced molecular equation that happens, all right? Magnesium carbonate is MgCO3, and nitric acid is HNO3. The magnesium and the hydrogen trade places, so you end up over here with magnesium nitrate, and anything with nitrate is aqueous. But initially, it looks like you have two H pluses and CO3 minus 2, which is carbonic acid, that H2CO3. H2CO3 does not stay H2CO3. It breaks down into CO2 gas and H2O liquid. And because of the gas, that's why they call it a gas-forming reaction. So this one right here is the balanced molecular form, showing all the reactants and all of the products. But in this question, we want the net ionic equation. We want to pull out spectators. Can anybody say here what the one spectator is for this reaction? The Mg is part of a solid on this side, and that is very close to being a spectator. But if something is involved in a solid, a gas, or a liquid, then it's not going to be one of the spectators. So like magnesium here is part of a solid on this side, and over here it's part of an aqueous. So it's like it's changing its phase, all right? So magnesium is close, but not quite.
Isn't it nitric acid?
Ooh, I liked half of your answer. Nitric acid does have the spectator in it. But notice here how hydrogen is AQ, and here hydrogen's in a liquid. So just like with the magnesium, which was in a solid and went AQ, the magnesium isn't a spectator, and the hydrogen part isn't a spectator either, because it's in aqueous here, and it's liquid down here. But I do like the nitrate part. Nitrate is an aqueous here, and nitrate is an aqueous here. So it's the nitrate part, which is the net ionic reaction. If you pull the nitrate out, so you'd have just 2H plus here, and you'd have just magnesium 2 plus here, this would be the net ionic reaction. And again, this conversation was really cool. Magnesium was in a solid and it went to aqueous. If it changes its phase, it's not a spectator. And the same thing for the H plus part of nitric acid, because H plus went from an aqueous to a liquid, so it's constant. But old nitrate just doesn't stand a chance. Nitrate aqueous here, nitrate aqueous here, nitrate right out of here. Sound effects not necessary. Cool questions. Any questions on this one? Okay. Another kind of reaction we've looked at a little bit already, and this is called a combustion reaction. And we looked at combustion reactions last week, Monday. In a combustion reaction, It's used a lot to identify organic compounds. And in a combustion reaction, you have something organic and you're burning it in O2. And those are the only reactants you're going to have. And the products of a combustion reaction will always be water and carbon dioxide. So for a combustion reaction, sometimes I'll write CXHY, and you can even put OZ if you want on there, because some of them have oxygen. It burns in O2, and you make CO2 and water as your products. So combustion is just a fancy name for burning, all right? And you're burning the organic piece. You only get water and carbon dioxide. Sometimes if you have nitrogen, you'll get nitrogen dioxide, but honestly, that's nothing to be too worried about. So some examples of this, here is a compound called ethene, which you don't need to know. It's something organic. It has carbon and hydrogen. You're putting oxygen in, and the only products are water and CO2. So you can balance this reaction out, 2 carbons there, 2 carbons, total 4 hydrogens means you'll need 2 waters, etc., etc. You can have bigger compounds than this. This is a compound with carbon, hydrogen, nitrogen, and oxygen. And again, the products, almost always water and CO2. This one, because it has nitrogen, would have nitrogen dioxide too. This is honestly something you don't need to worry about, but it is something you might see. Again, you're taking something organic, burning it in oxygen, water and CO2 will definitely come out. In this case, you get some NO2 out. You don't need to worry about that. Questions? Chemists use this kind of reaction when you want to identify unknown organic compounds, because if you burn these things in a combustion reaction, you can use it to find grams of CO2 and grams of water and back calculate what the formulas are, stuff like that. So this is the 4th kind of reaction. This one is not an exchange reaction. And I should point out that the lab on Wednesday, we're going to look at the first 3 types of reactions: precipitation, acid-base, and gas-forming reactions. So they will all be the exchange where the metals trade places with the cations and non-metals trade places. The 4th type is this combustion reaction. The 5th type...
Purple solution is aqueous potassium permanganate. The colorless solution contains iron 2+ ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2+, and the iron is oxidized to iron 3+ ion.
This 5th type of reaction is a type of reaction I can't really have like a quick and dirty little equation like I did for these 4 up here. And this 5th type is called a redox reaction. Now, redox is an abbreviation for what really is reduction and oxidation. So sometimes these are called oxidation reduction reactions, or because chemists are lazy, we call them redox reactions more often than not. And a redox reaction is a reaction that involves electrons being transferred. Now, all of these examples that we've looked at so far, the atoms would trade places with each other, but really the electrons were the same. So like in the precipitation reactions with iron we saw, iron was +3 on the left and it was +3 on the right. So iron keeps all the electrons it has. It doesn't gain electrons to become +2. It doesn't lose electrons to become +4, something like that. In redox reactions, things will trade electrons, and we'll talk about how to see it. Now, this KMNO4 iron reaction down here is a good example of a redox reaction. You took that purple KMNO4 and some iron, and you actually change its electrons around. This is an example of making water, and believe it or not, making water from hydrogen and oxygen is also a redox reaction. So being able to figure out when electrons are being transferred is a big part of figuring out if you have a redox reaction. Redox reactions, arguably, are the most important of the 5 types of reactions, but it's very, very broad, as we'll see here in a little bit. Leo is my friend on this section, and Leo is a lion, as you can tell, and Leo says, "Grrr!" And besides me, you might be thinking I might have lost all my marbles, which is always a possibility. Leo says Gerd is actually an acronym, and it can help you when it comes to oxidation and reduction. So Leo says Gerd is really helpful to chemists. Leo stands for lose electrons oxidized. Gerd stands for gain electrons reduced. So something that gains electrons is reduced, something that loses electrons is oxidized. So here's two examples of some metals. And then the first one, zinc, is going to zinc 2+, and copper 2+, and the second one is going to copper metal. Notice how I called copper metal copper solid. If the element has all of its electrons and protons and it's a metal, then you can say just like copper metal. This would be a copper ion because it doesn't have all of its electrons. Anyway, oxidized and reduced is always relative to the reactant, and that's really important. So what we're going to do here is figure out if zinc metal is being oxidized or reduced. And notice how zinc on the left is 0 charge. There's no positive or negative. But on the product side, it has a positive 2 charge. All right? So zinc has lost 2 electrons. It has become more positive. So that's what it means to be oxidized here. Zinc has lost electrons. It went from a 0 charge to a positive 2 charge. And remember, when it comes to electrons, it's different than money, all right? You become more positive as you lose electrons. If you have money, you gain money, you become more positive in the bank, whatever. Money and electrons don't work, so don't use them here. Here, zinc is going from a 0 to a positive 2. It's being oxidized. I actually put the electrons in. Remember that electrons are -1, so you have 2 -1 electrons coming, and that makes zinc +2. Now, on the other hand, copper 2+ going to copper metal, copper here is gaining 2 electrons. The copper 2+ is being reduced. Copper is becoming less positive, more negative, all right? And that's because it's gained 2 negative electrons to become neutral copper. So zinc losing 2 electrons, zinc has been oxidized. Copper 2+ here has gained electrons, 2 electrons to become copper metal. Copper 2+ is reduced. And remember, oxidized and reduced are always relative to reactants. Don't start thinking about zinc 2+ going to zinc. You'll get yourself all mixed up. It's always relative to reactants, those things to the left of the arrow. Now, if you've taken chemistry before, you might have heard about oil rig, all right, and oil rig is fine too. Oil oxidation is losing electrons, so zinc has lost electrons. Rig reduction is gaining, so the reduced part here is gaining electrons. I don't personally like oil rig as much as my good old Leo the Lion Sanger, but it's up to you which way to go, and I'm sure there's other expressions out there. If you have other cool expressions that your dorky instructor would like, share them with me. Questions? Okay, so let's see some examples now of how we can figure this stuff out.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
This is kind of a neat reaction. This is a time-lapse photography video. I'm showing it over many times. They started with a piece of copper metal, which is used in like wiring for electronics. And they have in there a solution of what was silver nitrate. But the nitrate here is a spectator. We don't really care about the nitrate, so I'm not even including it. So the nitrate's excluded. And what happens here is the copper metal actually turns into a copper 2+. And this blue color right here is really indicative of the copper 2+ ion. It's a really neat kind of a blue color. Now, on the copper metal itself, you get this kind of mossy looking stuff. And this mossy stuff is actually pure silver metal. Initially, when metals form, they don't make like necklaces and stuff like that. It comes out in a very raw form. And silver looks to me like moss on a tree or something like that. So this is actually silver metal, and it's deposited right on the remaining copper metal itself. So this is a redox reaction, all right? And we know it, and you'll know it too, because there's charges, the charges on the metals here are changing. So copper here is 0 initially on the reactant side, and it goes to copper 2+ on the product side. It went from a 0 to a +2. This one became more positive. And in a redox reaction, if something becomes more positive, there has to be something becoming more negative. And if you look at this long enough, the silver plus ions in silver nitrate became silver 0. It went from a +1 to a 0. It's becoming more negative, if you will. So the electrons are going from the copper to the silver plus. And I know that because copper ends up losing electrons, it becomes more positive. Silver plus is gaining those electrons, it's becoming more negative. It's becoming neutral silver. It's not going negative, but it's more negative than it was as a positive thing. So as a chemist, all right, you can figure this out in the way I just did. And, oh, copper is becoming more positive and silver plus is becoming more negative. And for some people that works, all right? But what I'm going to do next is talk about oxidation numbers. And those are sometimes better ways to figure out if you have a redox reaction. But the highlight here of a redox reaction is that if you have something being oxidized, you must have something being reduced. Because that oxidized part is going to be losing electrons. And electrons don't do well in the wild. You can't usually like cage electrons and show them to your friends. The electrons have to be used up right away. And it's the reduced part which is going to take those electrons in. So the oxidized becomes a little bit more positive, the reduced will become more negative. You're always going to have both in a redox, and that's why they call it redox. It's reduction and oxidation. Something's reduced, that means something's oxidized, and vice versa. Questions on any of that? So oxidation numbers are just ways to figure out, but let's look at this reaction. It says here which one of these describes the reaction. And notice here how iron is going from a 0 iron to a +2, and the copper is going from a +2 to the 0. And if you see the numbers like that changing, the ionic numbers, that means you've got reduction and oxidizing going on. Now, remember that you have to have something oxidized and reduced in the same reaction. And if you look at these answers long enough, C and D don't make any sense. Because in this context, to have them both reduced or both oxidized would be kind of silly, all right? That would mean they're both losing electrons or both gaining electrons, and that's not how reduction oxidation works. You have to have something oxidized and reduced. So iron here is becoming more positive. It's going from a 0 to a +2 charge. And the only way it can do that is if iron loses electrons. Lose electrons oxidized. Leo the lion, iron is being oxidized. On the other hand, copper, +2 to 0 copper, it's having to gain 2 electrons to become 0. So -2 and +2 goes to 0. Copper 2+ gaining electrons reduced. Copper 2+ here is being reduced. So, if nothing else, all right, I want you to see that something has to be oxidized and something reduced in the same reaction if this is redox, all right? If you can take it to the next step, something's becoming more positive. That means it's losing electrons oxidized. On the other hand, you better have something becoming more negative, i.e. it's gaining electrons reduced. That's another way to see this. Questions? Okay. Oxidation numbers are ways that you can put numbers in front of elements and then see if something has been oxidized or reduced. So look at this reaction right here. It's MnO2 plus 4Al making 3Mn plus 2Al2O3. The numbers on the top correspond to manganese or aluminum. We're ignoring the oxygen for right now. So notice here, manganese goes from a positive 4 to a 0, while aluminum goes from a 0 to a positive 3. The hip chemist can look at these numbers and say, oh, manganese goes from a positive 4 to 0. Manganese is becoming less positive, more negative. Manganese is gaining electrons. On the other hand, aluminum here is going from a 0 to a positive 3. Aluminum must be losing electrons. Aluminum's being oxidized. So if you're having trouble with these, the oxidation numbers are great ways to see if something's being oxidized or reduced. If an element doesn't change, for example, when you figure out oxygen in both of these, it's -2 on both sides. If it's -2 on the left and -2 on the right, then it's not involved in oxidizing or reduction. So these things can be helpful. Some people like them more than others, and there's other ways to do this. So these are the boring rules for figuring out oxidation. First of all, this is important. It says that atoms as a free element will have an oxidation number of 0. So manganese here and aluminum are by themselves. There's no charge on them. That's why they're both 0. All the elements by themselves will have oxidation numbers of 0. So zinc is a solid, oxygen is a gas, bromine is a liquid, etc., etc. It doesn't matter if they're diatomic or monatomic. If they're an element by themselves, they're going to be 0. On the other hand, if you have what's called a simple ion, like chloride or magnesium, whatever the charge is equal to the oxidation number. So magnesium, +2, chloride, -1. And those are not only the ionic charges, but they're also the oxidation numbers. When it gets to a compound, then you think about it as the sum of all oxidation numbers will equal 0, or the overall charge. And in those kind of things, then you need to know some general rules. So if you have a compound and fluoride's in it, fluoride is always -1, oxygen is usually -2, and hydrogen is usually +1. There are some exceptions to these, but generally speaking, that's the case. And I'll show you an example here pretty soon of how you can use these to figure out the oxidation numbers on the pieces. So all of these rules right here, which are boring and probably a little esoteric at this point, are just ways to figure out if a compound has been oxidized or reduced. And if all the numbers on the left equal all the numbers on the right, then there hasn't been a reduction or oxidation. But what happens a lot, like in this case, your manganese is changing its oxidation number, and the aluminum is changing its oxidation number. So that means that something's been reduced and also something's being oxidized. Questions so far? Okay.
The atoms in hydrogen fluoride have oxidation numbers of +1 and -1 respectively. These are the charges the atoms would have if the bond were completely ionic. The oxidation numbers on the atoms of the perchlorate ion indicate the charges they would have if the transfer of electrons were complete. Such complete transfer, however, does not occur in reality.
Okay. So here's an example where you want to find the oxidation number of the H and the F in HF, all right? And it's not as bad as it sounds, but right now we don't know what the oxidation numbers are. So on the previous slide, fluoride is always -1 in a compound. And it can be any compound. Fluoride will always be -1. And usually in a compound, hydrogen is +1. So what you would do in HF is you'd initially say, all right, hydrogen's +1 and fluoride's -1. And once you've made these things, all of the oxidation numbers added together will equal the charge on the compound, if any. And HF doesn't have a charge. It's neutral, like NaCl or HCl or something like that. And notice here how the +1 on hydrogen added to the -1 on fluoride is 0. And that's good because there's no charge on the HF. So for HF, we would say the oxidation number of hydrogen plus 1, fluoride oxidation number negative 1, and again, both of those added together should equal the charge on the compound, which here is 0. Good to go. Now, perchlorate is ClO4 with a negative 1 charge. And in this problem, if we wanted to find the oxidation number of each one, what I would do here is I would start with the oxygen, because oxygen almost always negative 2. And in perchlorate, there are 4 oxygens. So I'm going to take the oxidation number for oxygen, negative 2, and multiply it by 4. Now, chlorine is all over the place. It can be negative 1, it can be positive 7, it can be a whole bunch of different numbers. So chlorine is going to be my unknown here. However, the 4 negative 2 oxygens plus whatever chlorine is going to equal negative 1. When I say that the sum of the oxidation numbers equals the charge, if any, on the molecule, in this case, perchlorate's negative 1. Up on the top, HF was neutral, so it was equal to 0, all right? But here, perchlorate is negative 1. So notice, you've got X, which we don't know chlorine, negative 2 times 4, negative 8 from the oxygens, and all of that equals negative 1, the charge. So if you put negative 8 on the other side, it becomes positive 8. 8 minus 1, that's how they got the positive 7 there for chlorine. I bring this up because if you use a periodic table that's one of the fancy laminated ones, sometimes you'll find in bookstores, they'll have these great periodic tables and they'll list the charges for chlorine and it'll say like negative 1, positive 1, negative 3, positive 3, all these different numbers. And it's kind of not right because those are oxidation numbers, all right? Those are when you have redox reactions, the possible numbers that pop up. So this is chlorine is positive 7. Now remember in the nomenclature lab, I was always saying chlorine was negative 1. And chlorine by itself as chloride is always negative 1. But the redox numbers, the oxidation numbers of chlorine in a molecule sometimes will be really weird. Like this one I consider to be really weird. Positive 7 chlorine, WTF in my world. But anyway, that's a very unusual kind of thing. So if you have one of those periodic tables, just realize some of their charges, quote unquote, are really oxidation numbers. They're not really charges per se. And oxidation numbers are helpful when you want to see if electrons have been transferred, but they're not really actual charges themselves. Any questions on any of this? Okay. So here's a reaction, aluminum and 3 coppers, 2 pluses, making 2 aluminum 3 pluses and 3 coppers. And the question is, in this kind of reaction, what's happening? All right? So first of all, if you look at just the gold reaction, notice how we have aluminum as an element going to aluminum as an ion. And we have copper as an ion going to copper as an element. If you see ions going to elements or elements going to ions, bam, you've got a redox reaction because none of these other 4 will do that. I mean, oxygen, arguably in a combustion reaction, I guess, is an element, so that would go to these 2. But those are kind of the weird ones. Almost all the time, going to be some kind of redox reaction involved. So if you know it's a redox reaction, then the question is, what's being oxidized and what's being reduced? Well, one thing you can do is you can pull the numbers, the aluminums down. Aluminum is a 0, aluminum is a positive 3, and it would go to 3 electrons. So aluminum here, you can see, has lost 3 electrons. Aluminum has become more positive, and that means that this thing has been oxidized. Oh, I forgot about this. Chemistry of redox reactions is very old, and sometimes things that are oxidized are also called reducing agents. Something that's oxidized is the agent which allows something else to be reduced. I really don't like this naming, but it is something you'll hear. So if you hear about reducing agent, that means something that's been oxidized. So aluminum has been oxidized, it's lost electrons. That means aluminum here is a reducing agent. Now, the other piece, which is copper, you can do the similar kind of thing. Copper 2 plus going to copper metal. Copper is becoming less positive. That means it's gaining electrons. Gaining electrons means reduced. And big surprise, something that's reduced also means it's an oxidizing agent. These are what they call half reactions, and in a half reaction you can show the electrons. But another thing you could do here, and why I brought it up, is you could use oxidation numbers to see what was going on. So 2Al and 3Cu2 plus going to 3Cu and 2Al3 plus. Elements by themselves, oxidation number is 0. So I can put a 0 by the copper and a 0 by the aluminum. On the other hand, the ions, the charge is the oxidation number. So this would be positive 2 and this would be positive 3. And notice how your aluminum is changing from a 0 to a plus 3. That's where this part really came from. All right, it shows that it's becoming more positive. On the other hand, the copper is going from a positive 2 to a 0. That's what's happening right here. Copper is becoming less positive, more negative, and it can only do that by gaining electrons. So, summarize redox. Very powerful type of reaction. It's lots and lots of things. I'll show you some examples, and there's millions more. In a redox reaction, something is losing electrons and something is gaining electrons. Losing electrons oxidized, Leo. Gaining electrons reduced, the Gerd part, all right? If something's oxidized, it's also known as a reducing agent. If something is reduced, it's also known as an oxidizing agent. I hate those terms, but I'm just the messenger. I didn't make these rules. As something becomes more negative or less positive, that means it's gaining electrons, because remember, electrons are negative. On the other hand, if you have something losing electrons oxidized, it will become more positive as it loses electrons. So any way you want to figure out your path through the woods here is awesome. And I'm hoping I've given you several different methods. You can figure out oxidation numbers and look for changes. You can kind of do the becoming more positive, becoming more negative. Any questions? We will look at this stuff more in problem set number 5, all right? But just realize that, yeah, figuring out if something's oxidized or reduced is kind of one of the parts of it.
Hydrogen monoxide is a colorless gas, which we can observe when we bubble it through water. When it contacts air, and therefore oxygen, an oxidation-reduction reaction quickly converts it to nitrogen dioxide, a visible brown gas. When heated iron comes in contact with gaseous chlorine, a reaction immediately takes place, forming a dark brown solid, iron 3 chloride. This oxidation-reduction reaction involves a transfer of electrons from atoms of iron metal to atoms of chlorine, a halogen.
Redox reactions are often spectacular. Really cool things happen. Gases turn color, solids start forming, et cetera, et cetera. And again, remember that something's reducing agent is oxidized, et cetera, et cetera. But assuming you've been breathing today in lecture, and I know you all have been, breathing itself is actually a redox reaction. The oxygen that we breathe in connects to the iron in our blood, the heme, and it's transported out. That's a redox reaction. And then as the oxygen is kicked out to where it's needed in the body, that's the reverse redox. So redox, pretty important. Go chemistry. Anyway, questions on? All right. The last section of this chapter we're going to look at is how to describe the strength of a solution. All right. So if you have, well, here's an example. If you've ever made Kool-Aid, all right, from the store, which I used to really love and stuff. And anyway, when my mom used to make it, she would follow the instructions exactly. And, 2 quarts or water or whatever, this much sugar. Well, I always liked my Kool-Aid kind of syrupy sweet. So instead of adding a lot of water, I would add maybe like half or 3/4 of the water. So when I drank it, it's like, wow, this sugar explosion in my mouth would probably cause me ADHD or something. But anyway, at least that's how I kind of liked it, all right? And the difference between my quote-unquote mom's Kool-Aid and my Kool-Aid is the concentration. It's the amount of sugar or Kool-Aid in the water. And this is really important to chemistry because you can have, for example, hydrochloric acid. It's so strong, it would like burn through your flesh. I'm sorry, it's getting Halloween. I must be getting a little more spectacular. But anyway, you can have super strong HCl, but you can also have really dilute HCl. And sometimes in lecture, if I'm feeling especially rambunctious, I will touch the HCl to show that it doesn't burn your thing. You want to wash it off with water right away, don't get me wrong. Anyway, I can do this kind of stuff because I know about molarity. And molarity, which gets the symbol big M, is just a way that chemists use to talk about the concentration, how much of the exciting part you have like in a certain amount of liquid. And you'll see things like 3.6 M. So the number in front is the concentration or molarity of the solution. So you could have 3.6 M Kool-Aid, all right, versus 1.0 M Kool-Aid. And the 1.0 M would be less concentrated, my mom's version of Kool-Aid. On the other hand, because I like this syrupy sweet kind of version of Kool-Aid for some reason, maybe mine was like 3.6 M, more concentrated, all right? So the bigger the number, the more punch your solute has, all right? Now in HCl, 3.6 M would be much higher concentration than 1.0 M. You wouldn't want to probably put your finger in 3.6 M. You wouldn't want to probably put it in 1.0 M either, but either way, it's you'd have more pain. I gotta get off this Halloween thing, I'm really sorry. You'd have more discomfort touching 3.6 M than you would have 1.0 M. Apologies, I'm gonna start getting back online here a little bit. Okay, prop that back on. Sometimes you'll see the number listed in brackets. That's older school a little bit. That's another way you'll see molarity. And when it comes right down to it, molarity, which is given again the symbol big M, molarity stands for moles of solute per liters of solution. Okay? So all of these things, 3.6 M would be 3.6 moles of Kool-Aid fuel per liter of Kool-Aid, something like that. Okay, that was a very weird introduction to molarity. Any questions about, I was going to say something else, but I can't think what it was. Let's go to this
To
example.
prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
So here's an example where you're making a solution, but instead of talking about Kool-Aid or hydrochloric acid, which for some reason I was fixated on, this is nickel 2 chloride hexahydrate, and it's a cool green kind of color. And what they did in this example is they weighed out 5 grams of it, and they placed it in this thing which is called a volumetric flask. Volumetric flasks have one line on them, and that line is pretty accurate in terms of volume. And you can see, if you look here carefully, the liquids usually have a meniscus, which is like a dip in the water. And the dip, the bottom of the dip, the bottom of the meniscus, if it's right on that line, then this would be like 250 exactly milliliters. That's kind of the idea. So anyway, they put this 5 grams of nickel 2 chloride hexahydrate. They filled it up to a total of 250 milliliters with water. We can use this information to calculate molarity. Okay? And a couple of things here. So molarity, which is capital M, not little m, by the way, we'll talk about that in Chem 222. Molarity, moles of solute per liters of solution. Now, let's go back. What is the solute in this question? What's the site? The nickel chloride, that's right. It's the NiCl2.6H2O. Nickel chloride is awesome. What is the solvent in this example? Water, that's right. Water is the bulk stuff, that's what we're filling in, that's right. And then the solution, in this case, would be the NiCl2AQ. So notice how the waters just kind of go off into the solution. We don't worry about those. And solute was a solid. I guess I could have written that in there. NiCl2.6H2O is a solid. Water is a liquid. But this one right here is AQ. So the solution, again, has the solute plus solvent. The interesting thing, the solvent is the bulk. It looks like a liquid at the end of the day. These three things are really important. So when we say moles of solute over liters of solution, it's just moles of the nickel 2 chloride hexahydrate. We don't care in this example how many moles of water there are. We just want the moles of the green solid. And the liters of solution, remember that's the whole thing. So that's why we're looking at where that little meniscus is on this particular dip. And the final thing, which is going to be really important, is you need to know how many milliliters are in a liter. How many milliliters are in 1 liter? 1,000, that's right. 1,000 milliliters equals 1 liter. Now, another way to say this, remember that milli is 10 to the minus 3. So 1 milliliter is 10 to the minus 3 liters. But you can convert this second one into the first one. You divide both sides by 10 to the minus 3. And on this side, 1 over 10 to the minus 3 becomes 10 to the positive 3, which is 1,000. So that's why I generally tell people to use this one, 1,000 milliliters per liter. But there's nothing wrong with using 1 milliliter equals 10 to the minus 3 liters. In these kind of problems, we're going to do a lot of this. We're going to do a lot of milliliter to liter and liter to milliliter conversions. So knowing this is really helpful. Any questions on this kind of background part? Okay, so now that we know solute, we know the solvent, we know the solution, we know milliliters to liters, we can start putting all this together. Because remember, molarity is just moles over liters. Moles of the solute, NiCl2.6H2O. So the first thing you do here is you need to find the molar mass of the nickel 2 chloride hexahydrate. So either using a periodic table calculator or by figuring it out, 1 nickel plus 2 Cls plus 6 waters, 6 times 18. That number came out to be 237.7 grams per mole. So if you have 5 grams of that, you can turn grams into moles. Grams over grams cancel out. You've got moles of the NiCl2 on top. 0.0210 moles nickel 2 chloride. Does anybody have any questions about where this number came from? Cool. Once you have the moles of solute, molarity again, moles over liters, moles of solute over liters of solution. So we'll take that moles, 0.0210, we'll divide it by the liters. Now 250 milliliters, remember that little dot right there means 3 sig figs. 250 divided by 1,000 comes out to be 0.250 liters. So moles over liters to 3 sig figs, 0.0841 molarity. So the concentration, or the molarity, same thing, of the nickel 2 chloride here, 0.0841 molar. Notice how here it's in square brackets, equaling this number. That's what you see sometimes, although that's not as common as it used to be. So grams to moles, milliliters to liters, moles over liters, Bam. Questions? Yeah.
So is that molarity, is that percentage, or is that just the standard unit?
It's a different kind of unit. Right on. A percentage in our class is usually mass percents. So it would be grams of something over total grams times 100, okay? Molarity is like a separate unit, all right? It's got moles, which is related to mass, but liters is volume, all right? So it's like a mole over a volume, a mass, if you will, over a volume. So it's a different kind of unit, that's right. There are ways to convert percentages to molarity and back and forth. We'll do that next term, but they are different things, man. Good. The other thing I would make sure this is a capital M. There's another kind of unit which uses a smaller m, and we'll talk about that next term. But for right now, just make sure that your m's are big M's here, and they are different from percentages. Good. Other questions? All right, this is a good place to take a break. It's about 10:57, so about 11:02ish. Come back and we'll keep knocking molarity down.